Hello, welcome to Spark Academy guys. Now today we will be going through electrical measurement and instrumentation lecture. In that we will be going through competitive exams as far as DISCOM exam is concerned or Transco exam is concerned all over the India, or ISRO and DRDO exams. The most likely asked questions on PMMC and MI we will be going through, and a few of the basic concepts regarding that. Now, first of all, what is PMMC? PMMC is nothing but a permanent magnet moving coil instrument, and EMI is nothing but only moving iron instrument. In this case, PMMC is suitable for DC and EMI is suitable for AC and DC. Now, in that case, what we will be doing is we will be trying to derive the equations of TD. TD is nothing but the deflecting torque. Deflecting torque here in PMMC is BINA. Here B is the magnetic flux density. Magnetic flux density. I is current through coil. N is equal to number of turns of coil, and A is nothing but area of coil. As far as this moving coil is concerned, the deflecting torque is given by this equation BINA. In that, now TD will be just equal to we are just rearranging the terms. Now, in moving coil, actually what happens is we are just rearranging the term in that flux density, the number of turns, and area of coil, which is equal because it is nothing but depend upon the material which we are using for the coil. That's why all this is constant. It is non-variable term, hence it is termed as constant. Only the TD will be proportional to I. I is nothing but the current flowing through the coil, and accordingly with respect to that current, what happens is that when moving coil is placed in a magnetic field, a kind of force is implemented or exerted by the coil, and that force is nothing but the torque. As torque is nothing but force into displacement, you know very well. Torque is nothing but force into R. Force into R. R is displacement. What is permanent magnet moving coil? A coil is placed in magnetic field. It will experience a force and displacement by that force is torque. Please note down because it is very important concept. No one will tell you in this language because it is a simpler manner to explain a torque. The coil is placed in a magnetic field, it will experience a force and displacement by that force is torque. Torque is nothing but force into displacement. Please note down this, and from here it is clear that TD, the deflecting torque, will be proportional to only current, hence its scale is uniform. The PMMC scale is uniform scale. Now in the same way, what we will be doing is we will be deriving the deflecting torque equation in case of MI. In case of MI also. Please note it down. And here the controlling torque is nothing but K into theta. K into theta. K is nothing but spring constant. Spring constant. K is nothing but spring constant. Deflecting torque is nothing but a torque which is being created by a pointer in order to give you a final reading. In this way, the pointer is deflected from 0 to max. This is nothing but a deflecting torque. And controlling torque, TC. TC is nothing but whenever you experience a kind of deflection and then the pointer comes to its rest position after some sort of pressure in order to maintain the equilibrium position of that pointer. In order to maintain the equilibrium position of that pointer, this spring is been acting in the opposite direction of the deflecting torque. That's why when at steady state TC equal to TD. Hence, you know TC is nothing but K into theta and TD is nothing but I. Just now we have calculated. Now let ignore this K constant. Theta will be proportional to I in PMNC. K is constant of spring. That's why you can ignore it. Only write the equation in form of theta proportional to I. It is for the PMMC instrument where the scale is uniform, or you can say linear scale. Please note it down very carefully. It will be asked in examination. Now I will be deriving the MI's moving iron instrument deflecting torque. And PMMC is used only for DC. Already I have explained you. Now for MI, what happens is, in case of MI, the moving iron instrument, soft iron piece is dragged into magnetic field. Hence, force of attraction and repulsion will take place to iron piece. This is nothing but a definition of moving iron instrument. Now, in this case, as far as magnetic field is concerned, you can write the equation for energy stored in magnetic field. In magnetic field, already we have studied that whenever magnetic field is concerned, we will be going through inductor concept. So energy stored in inductor, you know very well, the energy or work done or energy stored in inductor will be half L into I square. Already this equation is also been derived in the chapter of magnetic field. You can go through that lecture also. Now in this case, what happens is, we will just differentiate the equation, the equation. And when we differentiate this equation with respect to theta, the dw by d theta is equal to d by d theta in the bracket half Li square. The same will be written as half I square dl by d theta. This is nothing but the equation for deflecting torque. The deflecting torque. A mechanical torque is nothing but rate of change of stored energy. Rate of change of stored energy with respect to angle. With respect to angle. Rate of change of energy stored with respect to angle. Hence we have taken this as this is the torque equation derived for DYEE instrument. It is suitable for AC and DC as well. Now what we have to do is we have to just take this dl by d theta by 1 by 2 and I square. This term will be constant. This term will be constant, hence Td will be proportional to I square. And in the same way, you know the controlling torque is nothing but K into theta at steady state. At steady state, Tc equal to Td, hence K theta will be equal to I square. In this case also, please neglect this, ignore K here, it is constant, hence theta will be proportional to I square. Hence prove the Mi case. Hence K is non-linear, or you can say non-uniform. Just now I have cleared each and everything here, so please go through it. And also the scale is non-linear in the starting phase, and it is also known as crowded scale at starting or beginning for Mi. Please note it down because it will be asked in exam in MCQ also. And it is nothing but the energy stored in inductor, and accordingly what we have done is we have just differentiated the equation with respect to theta, the angle, because torque is nothing but rate of change of energy stored with respect to angle. So we have taken this into consideration and calculated the Td proportional to I square, or derived the Td proportional to I square. And here also K is the constant. K is nothing but the spring constant, already explained. Please note it down. Now I will be explaining you the damping torque. Damping torque is nothing but a resistive force acting against motion. Resistive force acting against motion. Now for PMMC instrument, eddy current damping is generally used. Eddy current damping is preferred, and for MI air friction and fluid friction damping is used. In these, oil is equal to fluid in many cases. Hence, the torque, you can say the damping torque will be proportional to omega, the angular velocity. And in this case of fluid friction, the damping torque will be proportional to nu into omega. This nu here is nothing but oil viscosity. Now I want to explain you that why this is damping torque is proportional to angular velocity, because actually if you go through the basics of physics, the damping torque actually will be proportional to only velocity, which is linear velocity, but when you take the angular concept, linear concept, it will be displacement in forward or reverse direction, but when you have to calculate the angular displacement, the angular velocity omega comes into picture. That's why what we have done is T damping will be proportional to R into this velocity, R into omega. R will come into picture, actually R into this, and it is proportional to this velocity will be proportional to R into omega. It is nothing but R square omega, but in that the R square will be constant. That's why we are taking damping torque is directly proportional to omega. This is nothing but the analogy for damping torque. It is not asked actually in exam, but I am giving you in order to clear your concept regarding the damping. And at steady state condition, omega is equal to 0, as angular displacement will be 0, hence damping torque T damping will be 0 at steady state. This will be asked in exam. So according to the equation, we have just proved why the damping torque is 0 at steady state condition. As the basic equation, you know why this has been happening, because torque is directly proportional. Torque is nothing but force into displacement R. The F damp force will be velocity. Hence we are taking T damp is equal to R into omega, and we are R into velocity, Your velocity will be again r into omega. The basic formulas, never forget the basic concepts you have learned during your first year, second year diploma, or if you have done the 12th science, 11th science, 12th science. The basic formulas should be very important, or basic concepts should be by hearted, because you have to know each and every formulas, how they are coming across, and by time you will be helping you to implement that formulas during your derivations also, and during the concept learning also. It will aid you to acknowledge whatever the concept you are going through. Please note it down. Thank you for watching eSpark Tech Academy. As we have gone through a few electrical measurement and instrumentation things, and in next lecture we will be dealing with some sort of formulas regarding PMMC instrument, the sensitivity, how the range extension of voltmeter takes place, ammeter takes place, and the problems on that. Thank you very much. Please do like and subscribe the channel.